Now let's discuss about the nuclear stability. And this nuclear stability we can understand by using different concepts, and one of them is the neutron proton ratio, that is N by P ratio. So based on the N by P ratio we can understand the stability of the nucleus. So how we will get it? N by P ratio plays a vital role in deciding the stability of the nuclides. The N by P ratio is 1 in all the light stable nuclides up to calcium 40. Means whenever the number of neutrons is equal to number of protons, then for all those cases N by P value becomes equal to 1. Isn't it? The N by P value, the number of neutrons is equal to number of protons for the lighter nucleus, that is up to calcium, that is 20, calcium 40. And after that the ratio, that is N by P value, the N by P value, it will be more than 1. It will increase for heavier nucleus. What's the meaning of N by P value greater than 1? It indicates that the number of neutrons are more when compared to that of the number of protons. Isn't it? That is the reason why N by P is greater than 1. So why the neutron number is more when compared to the proton number? What happens is, whenever the atomic number is increasing, the number of protons inside that small nucleus increases. And whenever the number of protons increases, there will be more repulsions among the nucleus. And in order to decrease the repulsions between the existing protons, the number of neutrons increases, and that is the reason why the N by P value also goes on increasing. That's what I'm explaining here. Elements which are having higher atomic number, they are more stable. Elements with higher atomic number are more stable if they have slightly excess of neutrons, because these neutrons increase the attractive forces and also reduce the repulsion between the protons. So we are saying that up to atomic number 20, the number of neutrons as number of protons are equal to the same, for N by P value is equal to 1, and they are stable. And whenever we consider for higher nuclides, and they will also be stable only under the cases whenever the number of neutrons will be more in number when compared to the protons. What's the reason for that one? That is in order to decrease the repulsions between the existing protons. Let's move further for the understanding better. Now let us take the variation of the number of neutrons and protons for some of the nuclides with the help of a graph here. This is a graphical representation, and this is the axis where we are representing the number of neutrons, and here this is the number of protons or the atomic number. And see this white line, of course it's becoming blue now. This particular line, this line, what is this indicating? This is indicating that number of neutrons is equal to number of protons, and whenever number of neutrons is equal to number of protons, N by P value is equal to 1. Yes or no? Yes. Let's talk about this term called zone of stability afterwards. Then all the other which are present above this particular point, they are the cases where the number of neutrons are more, that is N by P value is greater than 1. Isn't it? N by P value is greater than 1, because this is the case where N by P value is equal to 1. And the one which are present below this particular line, all these particular, this entire region or this particular zone, this is the case where the N by P value is less than 1. So this is the one where N by P value is equal to 1. Here N by P value greater than 1, and here N by P value less than 1. Let's see what data we can get from this particular graph. Here it is. The stable nuclides which lie within the shaded area, and that shaded area we call it as a zone of stability. So this is the one, the shaded area. The stable nuclide which lie in this shaded area, in that particular zone we call it as the zone of stability. And the nuclides falling outside the zone, they are radioactive in nature and they are unstable. So those which are falling in this particular shaded area, that is in the zone of stability, they are stable. So it's not confirmed that, it is not concluded that wherever N by P value is equal to 1 in all the cases they will be stable. So that's not a conclusion. Only for lighter nuclides the stability is there whenever N by P value equal to 1, and for overall all the cases together, those nuclides which fall in this particular zone, that zone is called as zone of stability, they are stable. and all the others which are falling outside the zone, they are unstable, and that is the reason why they are radioactive in nature. And the nuclides that fall above the stability zone have excess of neutrons, just mentioned, because this is the neutron number increasing, and this is the part where the number of protons are increasing. So this is a zone where n by p value is greater than 1, and this is a zone where the n by p value is less than 1. In both the cases, the nucleates are unstable. Now, then these nucleates attain stability by making some adjustment in the n by p ratio. So we are talking about the stability of the nuclide. So when we are saying that those which are lying above this zone and below this zone with a different n by p ratio value, they are unstable. So how can they get stability? They can get stability by making some adjustments in the n by p ratio. How can they do the adjustment in n by p ratio? Let's see. And concentrate here. This is very, very important for the objectives. So let us consider the isotopes with very high n by p ratio. So whenever the n by p ratio is very high, what does this indicate? More number of neutrons when compared to protons. And such a nuclide, they reach the stability zone by beta decay. What is the meaning of beta particle? Beta particles are nothing but the stream of electrons. So wherever we get the word beta particle, it means electron. So those which are having more number of neutrons when compared to protons, or wherever the n by p ratio is very, very high, they get into the stability zone, or they attain stability by undergoing beta decay. Means they will be giving out beta rays, or they will be giving out electrons. How can they give electrons? This is how they will be doing. The neutron is converted into electron and proton. So whenever a neutron is converted into an electron in proton, what happens? The number of neutron value decreases, isn't it? And as a new proton is formed, the proton value increases. So what happens overall? What happens? The n by p value will be decreasing when compared to that of the original value. So I repeat, those isotopes which have very high value of n by p ratio, they get into stability zone by beta decay. How beta particles are ejected there? It is in this way. A neutron is converted into a proton as well as an electron. That is how the number of neutron number is decreasing and the proton number is increasing. Take this case of first one, 6C14. Come on, find out the number of neutrons here. Number of neutrons, 14 minus 6. What's the value of 14 minus 6? And that is nothing but equal to 8. I am writing here n by p value, isn't it? N by p value for this particular example, this is equal to 8. Sorry, for number of neutrons is equal to 8. Then what is the number of proton? And proton value is nothing but equal to 6. Then what will be the value of 8 by 6? That is equal to 1.33. Let's see the case of the product form. 7n14. In 7n14, how many neutrons are there? A minus z value. A minus z value is equal to 7, and z is already 7. What happened? The value became 1. So because of that beta decay, the value decreased from 1.33 to 1. And in that particular way, it is entering into the zone of stability. Same with the case of the other examples also. Here is the second case. Let's understand what is happening for the isotopes which are having low n by p ratio. So isotopes with low n by p ratio, it means their proton number is more when compared to the neutron number. So here the nucleus contains excess protons, and they lie below the zone of stability in the diagram which is shown just now. And of course they are unstable, and such nuclides, they now need to increase their n by p value, isn't it? In order to get into the zone of stability, they need to increase the n by p value, and that can be done in 3 different ways. Previously there is only one way. Now we are getting 3 different ways to increase the n by p value. This is how. The first one, by the emission of an alpha particle. By the emission of alpha particle. What is an alpha particle? A helium nucleus. Double positively charged helium nucleus is called alpha particle. So here positive charges are coming out. Whenever the positive charges are coming out, the number of protons will decrease. And when the number of protons will decrease, definitely the n by p value will be increasing. So one way of getting stability for these kind of isotopes with a low N/P ratio, one is by emission of alpha particles, second one by emission of positron. What is positron? So this is the particle which is identical with electron in its mass and other characteristics, and it possesses a unipositive charge. That's the only difference. Electron is having uni-negative charge, whereas a positive electron, we call it as positive electron, that is positron, unipositive charge. So whenever a positron is coming out, a positive charge is coming out, so definitely the proton number will decrease and N/P value will be increasing. And another one is the K electron capture. So whenever electron is captured by this particular nuclide, again they will be increasing their N/P value. So those nuclides which are present above the zone of stability, they possess N/P value high and they attain stability by the beta decay, and the one which are present below the zone of stability, they will be having low N/P ratio and they can attain stability in three different ways. One by alpha decay, second one positron emission, and third one is the K capture. K capture means that is addition of or accepting electron into that particular atom. So that is how we can explain the stability of the nucleus in terms of N/P ratio. Alpha emission is generally observed in natural radioactive isotopes, while emission of positron or K capture is observed in artificial radioactive isotopes.